All right, guys, go ahead and get started.
Yeah, I'm ready.
Okay. Our speaker today is Captain Ben Smith. He studied electrical engineering at the University of Arizona, computer science at the University of Alaska. He worked in Alaska for several years. Wrote a couple books on UNIX at one point, which is kind of cool, I didn't know. In 1998, retired from software engineering and began sailing on his own boat, the Mother of Perl. In 2001, he joined CCOM and brings us to today.
Thanks.
All right, thank you.
So what we're going to be talking about are some tools I wrote. It started off with some work done by a research scientist who was here, who now works at Google. And he needed to solve a problem quickly, and we were trying to get tidal data for doing a survey up in Castine, Maine. And he and his now wife, and Monica, who was in the class up there, I was feeding information down to him, and he had to convert the raw data from the tide gauges we had up there and give us something we could actually use for doing the survey work. So the basis of this is, I mean, we use tide data, for doing tide predictors. That's most people think of the tide predictors or just recording of real tidal data. But as mappers, we use it in our mapping. Nowadays, we map to the ellipsoid, and so there's another layer of abstraction or confusion or whatever you want between the reality and the data that we're collecting. But while we're doing our surveying, if we're surveying to the ellipsoid, we don't have to worry about the tides at that time. Later on, you do. But so these two, the problem is that this is what a tide predictor looks like. This is a NOAA tide predictor. I think it's for, I'm going to guess I used the Port Point in Portsmouth as for the data here. And this is a nice smooth lines, and there are no spikes or gaps in it. And that's because it's done mathematically. The tide predictors nowadays are based upon a Fourier analysis of tidal data, combined with, I guess a little bit of art form from historic tidal data, tidal predictors using the various constituents of tide, which is this whole business has been going on for hundreds of years. This is more like the real data, and this is data. This is data from Castine. It's a lot of points. You can see I have up here 376,000 data points in it. But you'll notice that these lines are not as smooth as one would like. There's these spots in there. There's some spots that are missing. This is what real data looks like. The problem is, how do we use this real data to do analysis of, we need to know what the water was at that point, at that time, and we may be missing data or there's a spike there. How do we clean this whole mess up? So these tools were designed for taking care of that. Right. So this is what we want to end up with. It's the same data set, cleaned up. One of the things that NOAA wants you to do to use their standards is that the data points are 6 minutes apart. This data was, I don't know, a couple of seconds apart maybe. I can't remember right now. But so we need to not only get rid of all these problems with the data, the gaps and the spikes and all the rest of that, we also had to resample the data so there's that 6 minutes, and it can't be just an arbitrary 6 minutes. It has to be 6 minutes precisely starting at the hour and continue on through the hour. So you have to make sure that's all aligned with the thing. But that's not We can't just take those data points at that time because they may not actually match up. And they may be off by a few seconds here, a few seconds there, so on. What do we have here? This is the problem we had in Castine, and we set a tide station. This would be too high, I believe. Right? Yeah, too high. So when the water was at low, it showed no water at all. And there's no way I can fix that with these tools. This is just bad installation of a tide station. So there's certain things you can't do with math. Right. So what I'm going to do is talk. These are the tools. I have a conversion tool, a trimming tool, an interpolation tool, a filter tool, downsampling, peaks analysis. So we're going to go through and we're going to describe what each of these tools does. And then we're going to go and talk about how it does that. So we'll talk about some of the math in it. And none of the math is very advanced. It's some basic statistics and signal processing stuff. If I can understand it, you can certainly understand it because this is not I'm not a mathematician. And then we have a whole slew of topics. Topics such as, why would you want to use a straight line interpolation rather than some other form of interpolation? Lots of questions. And these don't have, I don't have answers for these questions, but they're things to be thinking about if you're going to be using these tools or if you're going to write your own tools using MATLAB. I want to remind you, this is not written in MATLAB. And Jim Irish is not here, thank God, because he wrote a tide predictor in MATLAB. He knows this stuff way more than I do. But I have nothing against MATLAB other than the fact that it costs a lot of money and I don't have a license. I do like Python, which is the language I use for this. And it's freely available. And you will see later that I actually have it running on a Windows machine, despite the fact that that's not my preferred environment. As you can tell from the title of my book's on UNIX. So what I'm going to show you is the things you can do in Python. Python you can find on any operating system, any normal operating system, other than real-time operating systems. Okay. So let's talk about these tools. Okay, this is the conversion program. This is actually, as we'll find out later, is the only really complicated part of the whole program. None of these programs are very big. They're like, less than 1,000 lines of code, which, when I reached 1,000 lines, I started thinking, okay, this is getting complicated. And, when I reached 10,000 lines of code, I think it's a big program. That's a big program. So none of these are very big. They're just a couple of lines, a couple hundred lines of code, if that. And so this first one takes the raw data log and converts it to standard time and depth. And the standard is actually based upon the fact that we use Keras as our survey processing software primarily. And so I tried to match up with Keras's format for tidal data. But there are other options. There's several other options for the format you want to use. But we've used that in this program. I use that as a standard. Okay. The trim program, it's a way of either limiting the sample from in time, so it's here. That's the sample you want to deal with, or you can use the same tool. It will also do an analysis. A statistical analysis in order to find outliers and remove them. The interpolation tool, well, if you take out data points, you end up with holes there in the data in the time. So there'd be a time when you expect there to be a data point, but there's no data point. So you got to fill those in for a lot of these filters to work properly. You've got to have even increments of time to run through the filter. So this interpolation program is used actually here to fill in those spots, and then we also use the same program down here to resample it, which means say I was sampling at 90 seconds per data point, and we want to go to the 6 minutes. You know, so this same tool does those two things. It uses the same mathematics actually. A filter. This is filtering is you know, we can go on for you know, a week of lectures on just filtering alone. In fact, I was here talking to Colin Ware earlier this morning. He says, "Well, I don't see you have used the Fourier filter." And I said, "Oh, I never thought about it." But it's like I did try a bunch of them and tried to find the one that, you know, was the least complicated and produced the results that I wanted with the kind of data that we have. But you know, I mean, I should have thought about that. But after all, Fourier analysis is a major part of modern day tide studies. So here, downsampling is going to be the same thing as the interpolation program. But this is what we use when it's done. Used this way, it just does alignment, and you can actually upsample, meaning you can make it look like you have more data than you actually do. And then we have a program for finding the peaks, and we'll discover why that's not so easy. Because first off, it's fine if you have a nice function, mathematical function. It's fairly easy to what do you do? Do derivatives. Is that right? Yeah, to find peaks. But here we have a fairly complicated function, and we want to work with the real data rather than with you know, a derived tidal function, which is fairly complicated. And so we want to find the peaks. But if we have very noisy data, finding a peak in noisy data is impossible. So you have to make sure you have good, clean data before you get to that point. Right. So let's start with the tide convert. And here's some different tide station data formats. This is what the files look like. This is from an Endera, which used to be our standard. And this is, it's got a header, and it's got, and then you get these columns of data, and it's all textual. This is a Endera raw pressure. You know, it's just the Endera box, or a recording box, has been set up differently. Same box, but different configuration. This is Aquatrack, which I don't recall what technology is using, but it's probably a bubbler. Is that right? Does anyone know?
It's acoustic.
Aquatrack?
It's acoustic.
Acoustic?
Yeah.
Oh, yeah, there's a bubbler. Bubbler, you send air down a tube and see how much back pressure you have before the bubble bursts to figure out how much water you have. We use them in sounding the fuel tanks in the Coastal Surveyor. And this last one is on microwave tide gauge, which I guess it works similar to the acoustic, except it uses radio waves. I may be wrong on that. All right, so let's take a look. This is what we want to get to. There's a standard format for date, time, and some kind of height. And the truth of the matter is, we don't worry about the units for height here. You can use whatever units as long as it's consistent, and keep track of what units you are, so in case someone wants to go to meters, feet, or whatever. Most of the equipment we have and the way we have set up is set to measure in meters. This is also the Keras HIPS SIPS format. Okay, so that's what the tide convert program does. Now let's take a look at the tide trim program, which is looking for outliers. So here we have some missing data. We have some spikes that don't belong there. How do we find these? So this is what we want to end up with is we want to remove the blue spots that are wrong, and then we're going to have missing data points, which you can see here. There's no red spot there, and there's no red spot here, anywhere in there. So we're going to end up with some missing spots, but we eliminate the data that we don't want. So this is just to demonstrate again the missing data points. was now a tide resample. This is how to fill those spots. So this is how we do it. And this is what the result will be. So I'm using a straight line interpolation. So that's the last real data point. This is the next real data point, and then these are all the points that I filled in using a straight line. This is the filtering. So the blue data is the noisy data, and the filter, no, not very pretty, it has reduced a lot of the noise, and we might have to do some more filtering depending upon where we are in the scheme of things of the processing. But you can see how the raw data looks compared to the next filter. Here's a better example. By resampling at these spots, we can do some filtering that way as well. Okay, and then the peaks program, we're looking for highs and lows. And so this finds those spots, what the time is and what the amplitude is at those points. Yeah. It doesn't come out the way I wanted it to. Right. This has actually happened just a few years back with a student by the name of Sean Benny, who might give shivers up some people's spines, but nonetheless, his job was to try and do a comparative data collection of several different kinds of tide stations. So here we have what I call a radar, but I don't know, but that might be acoustic, I don't know.
That's the microwave.
That's a microwave? Yeah. And the NOAA's tide gauge is in this stilling well here, and I believe it's a bubbler, I'm not sure.
That's the acoustic one.
What
That's
is it?
the aqua track. Is it acoustic?
Acoustic, oh, this is acoustic one, okay. So this is the bubbler here, right?
Yes.
Okay. Thank you, Carl. Carl's our, by the way, is our NOAA tides person, if you don't, if you don't know him yet. I don't know what else we have here, but.
I think there's a GPS in the lab.
Oh. Hey. Okay, here's the problem with these different formats for data. So here in the red, we have a height, and in the blue and purple, we have date and time. This one does not have a date and time. It has another kind of timestamp, which may be what is called a UNIX timestamp. I'm not sure what they're using. Oh, seconds. It says right here, seconds of epoch, and the epoch might be the 1st of January 1970. Is that correct? That's a UNIX epoch, I think. The question is how to take all of these different formats and end up with the same kind of data. So this is how we do it. And this is why I say this is the most complicated part of all these programs. These are called regular expressions. And I don't expect anyone but a computer science student to understand regular expressions. They're a concise and efficient way of describing very complicated searching and matching patterns. So up to this point, we have, when everyone has a new tide data format, they come to me and I write the appropriate regular expressions for them, and then we go on from there. But hopefully with my first mate, Steve, this winter, and I will develop a format where you can write your own descriptions for tide formats using, I think maybe we'll end up using XML. It's a fairly standard way of describing stuff. And we'll get beyond that one problem, one glitch in the design. All right. This is out at Adams Point. If you guys haven't been out there, it's lovely. Okay, so this is the tide trim program. Now this is how the program actually worked. The problem is we have about a bunch of data points, right? This is, no, these aren't real data points, I just made up for this presentation. The question is this data point an outlier? Does it belong in the data set or not? So the way we deal with this problem is we take a sample of data, an even number sample on either side of the point we're trying to analyze. Okay? Then we define a line that's derived from the least squares regression, which is this line right here, through those points. Nice straight line. And then we make a little box that's one standard deviation or whatever we want. We can actually define what we want. I think actually I set it to 1.5 standard deviations away from this yellow line. So that's the test. Is it in the box or out of the box? So it looks like it's in the red zone, so we eliminate it. Okay. Now, how do we fill in the gaps? This is the interpolation method I use. So we can see we have some missing points. This is the points at which we actually have data here. But we don't know at this point, because we haven't given prescription to the program of what the data sampling rate is. We have to first do a little bit of analysis. So we take a look at the data points, and I just do this at the beginning of a file. I don't do this constantly over and over again. And then we find what's that, the median mode. Excuse me, mode. I'm not that good at statistics, obviously. So we find the most common interval, which is the green intervals here. Not the purple interval. There's only two of those. There's only one of the red ones. So we decide that's going to be what we're going to use as our standard interval for analyzing the data in the data file. So then we align that with the data that we have, and we find that we have some missing data points using that interval. The next thing we do is, for each of those missing gaps, we do a straight line interpolation, and we insert between here and here. Not a very good drawing. We say, oh, well, that's the intersect. Between here and here, that's the intersect, so on like that. Very simple stuff. And that's what we're going to use for our synthesized data. Now, the same program we use for what we call downsampling. So we're going to take a whole bunch of samples and then try to make them occur at some other intervals, some other interval rate. Interval, I guess it's not rate. So this is the upper ones are the ones we started with, and we're proposing to go to these 3 points here, this pattern here. Or somewhere by there. Oh, here's the red. The red lines don't even line up. Okay, so here we find we don't even line up with the blue lines. So we want our data now to appear on these red lines. The question is, how do we determine where that data point is going to be on the red line? So we begin by binning. I think that's the right term for this. But we look at evenly spaced time interval before and after each of the intervals we want to go to, right? And then we look at the data that's within that bin. So this is one bin, this is another bin, another bin. We analyze that data by simple averaging. Wink, wink, wink. And those are our new data points. Not that hard. But you have to get through, you have to do each of the steps. You can do this also by least squares averaging. Not a heck of a lot of difference, but you'll be able, I think I'll do a comparison here in a minute or two. No, maybe not. Most of these photographs, by the way, are from Nova Scotia, and I didn't take them. Okay, so here's another, here are filtering. So filtering is essentially kind of smoothing, right? There's lots of ways of filtering, lots of ways of filtering. The two I found useful that are, one is very generic and straightforward boxcar. Just, you know, you've got a square box of data. Every point has the same weight on it in that space. But what we have to do when we're doing this filtering is we got to make sure that we don't put any time bias. Nothing gets shifted in time by our filtering method. So I mean, some moving averages, this is a type of moving average, but some moving averages, if you just start moving the average and you start at the beginning and you run to the end, you're going to add a bias which is half of your averaging window. So the problem is we have to make sure that we don't have any time bias as a result. So here's our little window. We're going to look at the data in here, and in that window, we're going to analyze and filter. That point was moved because it didn't average using the boxcar averaging. This one, that's what happens, so on, right on down. And you can see that the average is moving on down the line here. Each of these points, these are the original points, these are the new points here. So you can see that these highs and lows from this process are smoothed out. But there's a problem. These red dots. We weren't able to do any averaging for those red dots because they were on either end of the window we were using for sampling. So the first, if we have a window that's this wide, the first point we can actually produce a result for is here in the middle. And the same thing happens at the other end. So these guys, we lose data at both ends of the data set. That's the cost. And so the original data and now the smooth data. You can see that the extremes have been taken out. Let's see how this goes. Boxcar moving average. I don't know why I did this. Just run through it. I'm sure it's entertaining. All right. The one thing, most of the other averaging or smoothing methods you use by averaging, moving average systems or methods, are a type of weighted average. So you end up, and we'll talk about this later if you have time, if you want to. So there are all these different patterns about what kind of weighting system to use, whether it's going to be you call it a Bayesian curve, that's called something, I don't know. You can use sine waves. You can use all sorts of other things for your weighting. Okay, so now we're going to take a look at how we do the peaks. And the way we do peak analysis is we look to see where the slope changes from up to down, and within a certain frame. And there's our little red frame moving along with us. And the tricky part of setting this thing up is finding a frame width that allows us to have peaks and determine them from noise. So there's a bunch of fiddling around with that, and empirical fiddling around with that to find out what is the best width for that analysis. Since we're not working off of a mathematical function, we have to just work with the data points that we have and finding that width so that we actually capture the peaks is good. Okay. that's the basis of the things I have to say. Now we have got these discussion topics. We can talk about command line and why I prefer to use the command line in doing my programming. We can talk about the filters. We can talk about downsampling techniques, interpolation methods. And so this is more, you guys have to kind of say what you're interested in and we'll move in that direction. Any questions?
How did you validate it? Did you take good data and throw things out or put in outliers and then?
No. I use bad data. I started with bad data.
Yeah, but you have to validate your techniques.
I gave them to Andy Armstrong. He said they were okay.
That's called an insensitive. But don't you need to validate it before you really have any confidence in it?
Yeah, you would, scientifically, yes. But I'm not a scientist.
Well, but you want to use it in the data analysis, the multi-beam bathymetry or whatever, and so you need to validate to make sure you haven't
Yes.
corrupted
Yeah.
the whole idea.
I mean, I think the problem we have here is this is a field data that can't be repeated. You know, I could take the filters and I could take good data and throw a bad data at it and then see what it come out with, which might be a good thing.
That's what I'm saying, yeah.
Yeah, I think it's probably a good thing.
What's
But
called sensitivity to
yeah.
take good data, corrupt it
yeah,
in a minor way, and then run all your analyses through it and see if you get the good data back.
well, it's never going to be the same because of your filters.
Well, that's an issue.
It is.
So that you have to determine what's the uncertainty that you've created in the data.
Yes.
Through all these techniques.
Yeah, I think we should be doing that this winter.
I think you should.
Yeah. You got to realize, I mean, Kelly introduced me and kind of told you all these different things I've done. Well, you know, I'm not really a professional at anything. I just having a good time. Yes, sir.
I mean, as a point of support here, one of the nice things that these tools provide is a modular system where, depending upon your constraints or requirements, such as verifying one way or another to different kinds of standards, you can write your own module for any of these steps of the system. You can write your own filter, you can write your own interpolator, and the framework is there already to help organize that process.
Well, Steve does have a bias. He's my first mate and has to say what I ask him to.
Thanks for the cookie.
Well, I want to hear your justification for using command line.
Ah, there! See, these two are connected. Okay, so we're going to go on the command line. Steve actually hit it right on the money. What happened here? I don't know. There's the discussion of filters. Let me go back this way. See if I can get back. There we go. There we go. Okay. One of the great values of command line is the fact that you can take a tool and connect it to another tool and to another tool, and you can modify the arguments to go from tool to tool, all with text, like with scripts. And this is not something that's easy to do, though there have been some noble attempts to do this. It's not an easy thing to do in graphical interfaces to software.
So all your programs read and write from standard in and standard out?
They can be, but if you notice here that I define input file and output file. So the parameters, I don't believe I'm using standard in and standard out, because I have error files that get generated. You know, when I'm going and doing a filtering operation, the data that's been filtered gets put into a file, separate file, so you can analyze it later. So I try to do that kind of, I have several outputs and maybe one input. And when you have an input, you can give it a whole list of files to process, and it'll process them one at a time. You know, there's a set of tools that some people may groan about. I'm very fond of, what took me about a year to figure them out, called generic mapping tools, GMT. And you want to talk about command line operations. But there's a value to this. You know, if you were to take all of these different, this is just the tide filter program, okay? And it's got, you can define a spec for, you know, the shape of your filter. If you want to just do a boxcar, the width of that. You know, there are all these different variables that you can add in there. And you can put these things into a menu system with a sub-menu to that menu for all the options to that. And pretty soon you've clicked this, but what the hell was that I was supposed to do over here? Whereas you can look at we're one set of arguments all at the same time when you're doing command line. It's ugly as sin, no question. It's not as bad as regular expressions, but it's well on its way. And I have to say that since I've been doing command line programming for using command line, well, anyone's been doing programming as long as I haven't had to do it. So, I mean, back since I think first time I actually had a command line prompt in a terminal was about 1975. So I admit that by being an old fart, and it just sort of seems like the natural way of doing things. But it's not that hard. And if you really want to be a hacker and get into systems, you got to learn this shit. I stopped myself saying bad words. Sorry. All right. Yeah. You have to learn this stuff.
So you bring up a great point, because if you use command line tools, you can script things, and if you can script things, then you can crank through lots of data in an automated way, or
Yes.
if you made a mistake, you can fix it all in an automated
Yes.
way, and you're not stuck pushing buttons all afternoon
That's right.
trying to
Yeah.
redo what you did.
There are certain things which I will try and show you. This is part of the Python tool set called matplotlib, which sounds kind of like MATLAB, doesn't it? And there's a good reason, because it has tried to take some of the best aspects of MATLAB. And this is a data set. It's over 1.3 million data points in it. This is from, let's see, I think this was from York Harbor. And this is the kind of stuff where you do want to have a graphical user interface. Notice, isn't that sweet? And there's some data. And this is the stuff we're dealing with. And this is the stuff we want to smooth out. And this is where we want to find if we have a maximum or minimum or just a piece of noise. And you know, and you notice the scales on the bottom. It started off with it's all doing. You know, it started off with days. Now we're talking about hours, minutes, and seconds. So it's all changing that. You can't even do this stuff with Excel. And this is free stuff, guys. It runs on any operating system. So. Yeah, this is when you want to have a graphical user interface, is when you want to do graphical things, like making graphs. All right, let me get back to where I was with this.
Can we look at your filtering in trials?
Which part?
Your filtering?
That image I had before. Let me get back to this. From cover slide. These parameters you talk about, what?
Well, you sort of briefly flipped through
Oh, yes, okay.
a bunch of examples of different filters that you
Yes, I'll do that. This, yeah. And then goes up to there. And that's this one here. How's that? This is, I don't remember where I got this graphic from, but it's showing you know, raw data versus the filtered data, showing you how, visually showing you the difference in the filter types. It doesn't have all of them. I think I may have looked a little bit here. Weighted moving average. Yeah, I don't think I developed this slide very much. Basically what you do is each of these points, instead of having an equal value assigned to it, it's equal to 1 times itself. You can say this is 1, because it's close to the point I'm analyzing, this has got a value of 1.5, and this has got a 0.14, 1.3, 1.2, and so on down out to the edge, and you probably want to be symmetrical in that. And then when you do you do your multiplication, your addition, division, and then it gives you your value. It just adds one more factor into the process. I played around with a bunch of those and really couldn't find anything better than just doing the straight boxcar for the kind of data we're dealing with. If you're working at gigahertz data sets coming out of sonar things, it might be a completely different game.
How big a window are you choosing for your boxcar filter?
By default, I believe I use 13 on either side. Has to be an odd number.
And you use 13 points regardless of the sample rate, or just 13?
It was 13.
Okay.
Yeah, but you can change it. I mean, it's just one of the parameters to the one of the arguments to the filter. You can put it anything you want, but the default value, I think I set at 13. More questions? Is there a party?
So when you get a data set, do you first look at it in that graphical user interface to kind of figure out maybe how you want to proceed with it? Do you do that first, or you just kind of do a simple plug and chug and then look at it to see how?
No, I like to look at the data like I just did with that thing that we zoomed in on. I like to look at things that you could, if you look at some of the data, like you see, because of the resolution of the screen and the plotting program, you see stuff that's irregular because the screen is very irregular. So if there's anything bizarre, it jumps right out at you just because of the fact it's being displayed on the screen. So I like to look at that. I'm a very visual kind of person, and then I'll say, oh, you know, well, we can't fix this one, or you know, we're going to have to, you know, spend some time working with the filters at some point. When I was working with bathymetric data, I worked with a lot of tools. I did those in Perl. This one's all done in Python. And I would use a tool called GNU-plot. And I could tell whether I had real bathymetric data or whether I was looking at waves, because the waves are fairly, boats going up and down, you know. And I don't have a, you know, this is in a dinghy, so I didn't really have a POSMD. Yeah. So, I mean, you can see stuff and you can kind of say, oh, look at that, that's way too regular. And, you know, it's, you know, or irregular or whatever. Yeah. Any more questions? That's pretty much it then. All right. Have a good weekend. Thank you very much.